Marco. All right, break out those notes. Let's get started. This is actually your first live calculus lesson in that one time that we tried to do it and it didn't work. Yeah. So I've had a. Yeah. Yeah. Blank down there. Oh, Carter's. Oh. It is. Yeah, he's
I need to make it. Dude, where's the mic? I need to blow into it. Oh wait, no. Oh, I don't have.
I can mute you if you can't find it.
I think he loves that. I honestly don't understand why feedback loops are so.
There you go. You're muted.
I'm on the meeting right now.
Okay. So yeah, I've had a little bit more experience trying to do it live lesson with geometry because that's what they do. So I just kind of go back and forth between working on stuff here and there. And Jackson, I thought that I didn't hit save. Third view lobby. Oh, welcome, Jackson. Okay, so if you take out your memory card and you take a look at the front side of it, pretty much shows you all the stuff that we have to do with parametrics. And that includes finding tangent lines because we need the slope, concavity, so we're going to need the second derivative. We'll need arc length and of all these parametric curves. So the first part of this is kind of understanding what a parametric curve is all about.
My bad.
My bad. All right. And then, so this is kind of, it says 10-1, but it's actually more than just 10-1 that's in the book because the next part is carrying that stuff over to vector valued functions. And it basically means that we're going to define the horizontal components separately from the vertical component and then define those based on time. So they're individually defined based on time. Okay, and that's what parametric is all about. I'm going to take the x and the y coordinate. Y is usually dependent upon x. But now what we're going to do is we're going to make y dependent upon some other parameter and x dependent upon that same parameter. Usually it's time, but it doesn't have to be. In terms of polar, then it's the angle that it's dependent upon instead of time. Okay, so think back to algebra 2, because that's probably when you had to do this. And you had to graph that equation. What would you probably do?
Find the zeros.
Find the zeros? Okay.
Find the vertex.
Find the vertex. We know how to find the vertex real easy now, right?
Sure, yeah.
Right. So we have tools that we didn't have back there in algebra, of course. So we could do stuff like, yeah, we can take the derivative. So y prime is equal to -32. That looks familiar. -32. Do you guys in physics use feet per second?
No, we use meters per second.
Meters per second. And then plus 64. You can set that equal to 0. And we have 32x is equal to 64. So x has got to be equal to 2. That's where your x coordinate of your vertex would be. And then you can stick that back into the equation. And then like there's certain points that you get. You might find the x-intercepts. You might find the y-intercept. What's the y-intercept of that one?
Oh,
It's 6, right? It took us a minute. It's like we're up here with math right now. We're coming back down to y-intercept, and we're like, I don't even know how to find that. I forgot. Okay. So yeah. So here's the graph. Again, this is y as a function of x, right? That's what we're used to. And let's say, for example, that we wanted to define motion based on this. When we define motion based on this, it was really not, this is not the path of whatever it is. It's like we're not throwing a ball or something like that. It's an up and down motion. It's a left-right motion. What's that called again?
Rectilinear.
It's rectilinear. Right. So for example, on this little graph, let's say I take this point right here. So that is at an x coordinate. It looks like it's about, what is that, 0.5? Yeah. So at 0.5, it looks like it's at about 30 right there. That means that it would have just gone straight up, say the y-axis at that point, right? And then it would keep going up, keep going up, keep going up, keep going up until it reached that peak of 70. And then on the other side, it's just coming back down, right? That's all it's doing. But now what we want to do is, what if I wanted the path to look like that? If I wanted the path to look like that, then I need another variable. And so usually, those of you who have taken physics, of course, you have like, think of a vector, you have a horizontal component and you have a vertical component. That's how we're going to define it. So we're going to define the x's and the y's based on another parameter here. Also, let's say if this was, I was trying to trace this out as a path of some sort of object, I would know where it was, but I wouldn't know exactly when it was there. Again, find a point, whatever that's on that parabola, but I don't know when it happened, like how many seconds. So I need to introduce that as part of this. And so that's what we're going to do. Right about here. So we don't know, we know where it's at, but we don't know when it's at until we introduce some sort of time to it. And that's where we're going to get some parametric equations. So we're going to take the x coordinate, define it based on some time or t, whatever this parameter is, and do the same thing with the y coordinates. And so instead of having a single function, you have a function for your horizontal and you have a separate function for your vertical in terms of your parameter. Which brings us then to parametric equations. Have you ever seen these kind of things right here? Anybody ever do any kind of designing or anything like that? Know what that is? They have little handles, and these little handles in this whatever this design software is, you can move the handles and it bends the curve. These are called Bezier curves, and it was invented by the French. It was a French car company, is Renault, and they did it to help them design curves for cars and stuff. And they're defined parametrically for these kind of curves. Okay, so let's say that, for example, I'm going to take that same exact equation that we had before, and we're going to turn it into a set of parametric equations. Well, part of it is I have chosen some sort of parameter, or maybe I'm measuring something. Again, if this is in terms of physics, maybe I'm measuring how the x changes with respect to time. Maybe I'm also measuring how the height changes with respect to time. And so here is an example of that. So you can see that x now is a function of time, and then y is also a function of time. So what actually, or a t, whatever this parameter is, what's the domain variable then? What's the independent variable for the parametrics? It's t, right? That's the thing that changes, and as it changes two things. It's going to change the x coordinate separately from the y coordinate. Okay, and so you can see that here's the domain for this particular one over here. 8 plus the square root of 70. I wonder where that came from. Yeah, probably. It's where it hits the x-axis, I think. Okay. All right, so let's see, like if you were going to plot this, if you had to do this by hand, it's back to algebra 1. The way that you plot it is you pick a t value here, maybe start at 0, and you plug it in here for the x, get a number, and you plug it in there for the y, get a number, and then you would plot that as an xy coordinate at that particular time. So you really have 3 things going on there, right? You have your x coordinate and your y coordinate and when it happened. So it would sort of look like this. Here's a table of values with all that. Would you want to do this by hand? Probably not. Sometimes what you have to do is you have to put this into your calculator because it has a parametric mode, but you may have to do 1 or 2 points so you can see what direction it goes, because that's one of the things that we want to know. As this t perimeter or this t parameter goes from 0, where's the laser pointer? From 0 up to this 8 plus the square root of 70, what direction is that particle moving along that curve? So it would look like this. So it looks just like the other parabola that we had before with the addition of an orientation. That orientation is marked with those little arrows that are right there.
Wait, so there's, you make 2 separate
Yes, you have two separate functions. One function for your horizontal separately from your vertical. So again, so it's like this. If I plug in 0 for my t coordinate for x, that'd be 0 divided by 4. You have an x coordinate of 0. If I plug in the 0 in here for the y, 0 plus 0 plus 6 gives me 6. I plot that as an ordered pair right there at 0, 6 at t equals 0. Again, it gives me that extra piece of information of when it happened. You plug in 1. If I plug in 1, I'd get 1/4 for your x coordinate. If I plug in 1 here, it's what, -1 plus 16 plus 6, which turns out to be what, apparently 21. And then that would be another point. This one went up to 2, 70, which is not in our table, but that happened at 8 seconds. You can see that's beyond this here. And then keep on going. And we can see again the path that this thing is going along from one side of this thing to another side. Yeah.
So the T is more like the distance along the line? Like you can't really see it from like a grid standpoint?
No, it is some sort of parameter that could be, like I said, it just depends on the application itself. The most common one is time. And when we get to polar, it's going to be an angle measurement that happens that changes our X and our Y. So in this instance, if we think in terms of physics, that T doesn't appear on the graph at all, right? There's no T version here because this is an X direction, that's a Y direction. So we don't see the T happen at all. It happens in this background where we're saying that once I've plotted that point, it came from a T value, that parameter that I've plugged into the equation, so I know it. But it doesn't, so like this 8's not on this graph anywhere, right? T equals 8, it's not on this graph at all.
Is it just a coincidence that the y value at t equals 8 is the same thing as the conditions for t? 8 plus square root of 70, since t equals 8 at 2, 70?
I don't think that was a coincidence, no. All right, we've been talking about up until this point, this whole entire year, rectilinear motion. And it was essentially just back and forth motion on an axis. That's all we could do, and that's all AB ever does. Now we get to do basically two-dimensional motion, where we are moving horizontally versus a vertical component against a variable of time. And that's called curvilinear motion. And so now when you see this graph actually is what the path of that object looks like. It looks like this parabola. When we saw the parabola for a rectilinear motion, it wasn't. It was just measuring its height versus time. So maybe just bouncing up and down, straight up and down, but this one's actually moving a combination of left and right and up and down. Okay. Now, that parameter there, that t over 2, it didn't, or that t over 4, it didn't have to be that. Maybe they change it to something else. That actually does not change the graph. It just changes when the points occur on that graph. Does that make sense? We're going to see an instance of that in just a minute. This is called a plane curve. So a plane curve is just the graph of a set of parametric equations. And we have defined each one of these components, the x coordinates, as a function of time. The x coordinate separately from the y coordinate. They've got 3 more minutes on this. Okay. Now, for the most part, you're not going to have to plot any parametric equations, but it's a good idea for us to get a grasp of how those graphs are made, and some vocabulary that's associated with them. And a lot of these things are calculator active questions, so we'll spend some time being able to put them into the calculator. It's probably a mode that you have never ever touched on your calculator ever, parametric mode. There's also a polar mode as well. Okay, so there's those. So here's that wherever it is that we start, which is at the lower end of your parameter, you plug that in, that gives you your initial point. If this is in terms of that curvilinear motion, that of course is where it starts, right? And then the last point there, if you have terminal cancer, that means you're going to die. This is the end, right? This is where the thing ends. Or I guess you could say the term, like a terminal on a airport.
You don't have to go so deep.
Or so dark. Okay, and then the arrows there indicate the orientation, the direction that the particle is moving from one part of it to another part. All right, so now I'm going to flip over to, do you guys remember back in the day in geometry when I'd use Geometry Sketchpad all the time? Yeah. All right, so I'm going to flip over here to Geometry Sketchpad on the computer. So we can play around with it. And why don't you go ahead and grab your graphing calculator, find your mode button, and then see if you can switch it to parametric mode.
This has been here the whole time.
Right? Okay, wait. Let me see.
Things on the calculator.
Well, it's never come up because you've never learned about parametrics. You ordinarily learn about it in what is that class called?
Pre-cal?
Pre-cal. Yes. Okay. Okay. So whenever you do switch the mode here from function to parametric, let's take a look at how things change for the calculator. So whenever I select that mode and I quit back out of it, that's right. You hit your variable button that you're so used to having X. It's not anymore. It's a T. The variable button. It's the one that's the X button that we always just say, oh, hit X. And so you just hit that button. Right. Yes, that's correct. All right. It's T now because that is the independent variable for our parametric equations. Now, not only that, hit y equals now.
Yeah, I already probably.
So when you go into y equals, you will see a component for your horizontal separate from your vertical. So maybe type in the same one that we were working with, which was a t over 2 or t over 4. Hit enter. And what was it? Negative t squared plus 16t
Yeah, maybe that. Did a minus by accident.
plus 6. I did. Was it plus? It was plus. And then plus 6. All right, if I hit graph, I may not see anything because of what the graph screen is set to. So I may have to change my window. So let's maybe go to the window settings. And now you have something else. You have your T-min and your T-max because that's the independent variable. So maybe, oh, am I not sharing the screen on this? Oops. Yeah, sorry. Okay. So ours started with 0, which was good. And this one looks like it's, is that what, 2 pi? Oh, it looks like.
Yeah.
It
normally goes from 0 to 2 pi.
Yeah, probably right. So let's put in, was it 8 plus the square root of 70? Okay. The step, I'm not even going to mess with it. Our x minimum is probably going to be 0 here. And the max, remember from the graph, it was up to 70. I don't know. Maybe I give it a little bit of breathing room. 72. Here, let's make it 80, and then I can go up by 8. That sounds good. Y minimum, we'll go to from 0. Wait, that's not right. I had my y's and my x's. Yes. That should be 0. This should be 80, and that should be 8. So what should x's be? We'll go to 8. And then maybe a scale of 1. I don't know. Let's hit a graph and let's see. Window range.
Oh, it's because you did 80 to 8, not 8 to 80.
Did I really?
Everyone know, yeah.
Did I
was gonna
really?
say something, but I thought it was right, and I don't want to mess it up.
Minimum is 80 and my maximum is 8. Awesome. So the 0. What's so the pizza should be here shortly, so you just have a seat and wait. Did you just make sure your name's on all your stuff and stuff? Okay. All right then. And I see you guys on Monday, right? So I'll try to have all that stuff graded by then so you get some feedback and start the process. Yeah. Okay.
Thank you.
Why is it wobbly?
Oh, sorry, why not?
It's like slightly disoriented. Yeah, look at the left. Yeah, there's like a dip in it.
Oh yeah, I see. It's screen resolution or something. Maybe if we had changed our T step size, it would have increased the resolution by a little bit. Okay, so now then, let me get over here to geometry. Series, not series.
Yeah, so I changed my I scaled 3 XR.
All right, so here's that. I want to say this is that same graph. Unfortunately, the screen that I make this at home on is a little bit bigger than this one, but I can move my t value. As I move my t value, you can see the points moving along our parabola near that curvilinear motion. And this is the same one that you just graphed. All right, so now I'm going to do the same thing, but look at what I did for the parameter. Now the parameter, or the x coordinate, is x divided by 2. So now watch what will happen whenever I move my t.
It got wide.
So no, the graph is exactly the same. I have just moved it a little bit. So what happens really whenever you change that x to a t over 2?
You move less. Wait, that's
What's that?
You can move.
You move faster, right? So it has all the same points, but they all occur before the t over 2 or the t over 4. They occur sooner. All right, so here's a couple more. So what I'm going to do on this one is I'm not going to show you the graph. I'm just going to let t go from 0 to like whatever and watch what happens with your graph. Really hope that we can see the whole entire thing. So there we go. Here's the graph, this parametric set of equations.
Any doing cursive.
It does look like cursive. That is correct. All right. So are you ready to see what it does look like then?
Is it your name?
Yeah, I wish.
Keep the words.
So that is one that you could type into your calculator too. Of course, instead of this is just the way the program works. It does it in terms of x's. You would have to still do yours as a t plus sine of 5t, and your y coordinate as a t plus sine of 16.
That kind of looks like my last name.
Sort of does. Maybe this is how you sign your name from now on.
Maybe.
Sign functions. Yeah. Oh, no.
It's meant to be.
All right, so you get some pretty trippy graphs with, you have some capability of making some very trippy graphs. Here's another one.
What is the other one?
Looks pretty chaotic, right?
I'm scared.
This guy.
Brenda's asking how many people this was.
I want to say there was 18. All right, let me move it back.
I thought we were having 20. I'm sorry. Honestly.
All right, you ready to see it?
Yeah. Oh, that's cool. You do murals. They said that we got 16.
Was it 16? I could have sworn it was 18.
You said 16, 18. That's funny.
It's enough pizza.
No.
I get money for it.
Yeah. It's. I hope they skipped on the Hawaiians.
Yes.
That sounds bad, I guess.
I had them skimp on the ground beef for personal reasons.
Yeah, I mean, thank you.
Okay.
Brendan's missing like everything, or mine's being blown.
Did you try graphing that cursive one on your calculator?
I grabbed this. Looks kind of funny.
Resolution on the calculator is not going to be as nice as it is on the PC, of course.
You gotta change your.
How long is the parametric?
Oh, so we're just doing 2 lessons. I cram it all into 2 lessons, even though it's more than 2 lessons in the book. Okay. So here's that one, and here's that one. Awesome, awesome, awesome. Okay. So for a regular rectangular equation, there is not a single, as in a unique representation in parametric equations. You can define it in infinite number of ways. It just depends on what it is that you select, how you want to select your parameter. All right, so this one was the second one. And then the nice thing about this, I put a table of values to compare them back to back. So if you take a look at t equals 2 for the second one is the x coordinate happens at t over 2. And notice that that point 1, 54 is someplace else on this table. When does it happen?
At t equals 4.
At t equals 4, right? It happens at t equals 4 for the other one, because you're going to have the same exact coordinate. If I plug in 2, if I come back over here, if I plug in 2 here, I get 2 over 2 is equal to 1, x coordinate of 1. If I come back over here to this other one that we defined initially, oh, it's right over here. 4 over 4 is a 1. It's just that the other one happens a little bit sooner, right? Okay. All right, the next thing that we're going to do is talk about like how you're supposed to graph it. If you were having to graph it, step number 1 is to turn your calculator on. Hit the mode button. No. If you had to do it by hand, it's what I was saying is that you have to do it Algebra 1 style. You make yourself a table of values, some sort of table just like what we saw right here. Increase your value of t. Now, t is a continuous variable. So we're only picking like some integer ones just because that's going to be easy to plug in. But we would know that we would get all of the stuff that's in between there, right? And then graph that as a set of ordered pairs and connect them and make sure you pay attention to the orientation, what direction it goes in. Yes?
Could you solve for t on one of the equations and plug it in?
Yes. Now, sometimes you get something that is too hard to graph by hand. So what you're talking is about eliminating the parameter, which is another way to graph it. You eliminate the parameter, you graph it as a rectangular equation, and then you have to go back and do this part where you try to see what the orientation is. Where does it start? Where does it finish? So I can see what direction it's going. I can't always do that because I'm going to get some pretty crazy looking graphs. You want to solve for that cursive looking one? It's not a function. It's not even close to being a function, right? Yeah, so I highly encourage you to give that a try. Eliminate the parameter there. Okay. So let's see if we can graph this one start to finish on our own, right? So I'm going to flip over here because I think I whited out the whole entire graph. We're going to see if we can do it on our own. I thought I whited out. Okay, so pretend like you cannot see this so that we could do it on our own. Let me pull up a white sticky. There you go. Look at that. Exactly. Right. Okay. All right. So it gives us a domain for our t variable. So we're just going to start at 0, go up to 4, see what happens. We're going to make ourselves a little t chart. Oh, do you remember the days when that's the only way you knew how to graph stuff? Before SRT transformations, before calculus. Okay, so we'll start with a 0. If I plug a 0 in for my t, I get 0. If I plug a 0 in for my y, 1. So whenever I go to graph this is going to be glorious, especially if I graph this on top of that and I pull the the thing away. All right, so it's at, so I'm going to say that's 0, 1 right there. All right, so then let's say that I stick in the number 1. If I stick in 1, 1 minus 2, I get an x coordinate of -1. I plug in a 1 for the y, I get 2. So -1, 2, it's over here. Plug in a 2. Get 0 again. 3. Yes, that is that's right. That's not how functions work. So you remember when, let's say, for example, you wanted to graph a circle in function mode. It doesn't work very well. You had to turn it into the top semicircle and the bottom semicircle. And then also whenever you go to graph it, it has a hard time right around the x-axis where you have those vertical tangent lines. But you can do it parametrically, and it'll graph it perfectly. Or in polar mode. Okay. Anyway, so let's say 3, plug in 3. 9 minus 6, what do we get? 3? And 4? 1, 2, 3. 4, right up there. And
5. Whoa. Oh, sorry, I skipped 2 again.
you wanted 5 over here.
Yeah.
What about for our x coordinates? So we got 16 minus 8. We get 8.
I probably missed some of that, honestly.
I'm going to say it's about right up here. All right, so notice that we started over here at this point. So this is our initial point, and then we're looping around. So let me make sure. Watch this. Let's see if this does that. Did you see that?
I'm so excited for the reveal.
Yeah, and then you got little arrows, right?
Yes. So the only thing that I now have to do is I got to put some arrows to indicate the orientation, something like this. All right, are we ready for the reveal? Let's see how good it was.
The shame, you can't see it.
Why is that? That's crazy. Oh, it's probably, no, it's because it was on the piece of paper that I put there.
Oh,
So,
that's very
yeah.
sad.
All right.
I'll never be able to see. You can screenshot it, then delete it, and it'll be good.
Yeah, there you go. All right, well,
Yeah.
there it is, step by step, ba-doom, 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 plotting points. All right, but you can see that it does look like a parabola, or at least part of a parabola. So just like Peyton says, one of the things that we could do is just turn this into a rectangular equation. It would not be a function. It would not be a function of x. Instead, it would be a function of y, all right, because it's a sideways parabola. I think that's what we're doing next, right? And that's called eliminating the parameter. So eliminating the parameter, you get rid of it. So you solve, it's just by substitution. You solve one of the equations, whichever one's easiest for t, and then you plug that into the other equation, bam, it's gone. It's just like, again, it's algebra 1. You do substitution and elimination.
It's not the elimination that you bring there.
Yes, it's not the same kind of elimination. You're correct. Okay. All right, so our equations were x is equal to, remind me. That was it?
Yeah.
Okay. And then the y was equal to t plus 1. All right. Which of those is obviously easier to solve for? What?
Factor out a t?
All right, so I've got t is equal to y minus 1. And now we'll take this y minus 1 and cram it in for t right up in here, right? So I have x is equal to, parentheses, y minus 1 squared minus 2 times y minus 1. You could leave it like that. Or maybe you expand this thing out. Y squared minus 2y plus 1 minus 2y plus 2. X is equal to y squared minus 4y plus 3. There you go. Does it look like a parabola?
Well,
Yes, it's quadratic in terms of y instead of in terms of x, right? So sometimes, like, one of the things that we're going to do on this stuff is the calculus that we've learned to do on rectangular equations, like taking the derivative, taking the second derivative. But we're always going to start with, to try to understand it, by eliminating the parameter and then look at it as a rectangular equation and then see if we can get the parametric version of it. Let's see how that thing compares. All right, so that's exactly what the elimination looks like. Take your parametric equations, choose one of them to solve for t, whichever one's the easiest, substitute that into the other equation, bam, algebra happens. So
when would you use them?
let's say, for example, so what Peyton said was one of the ways that you could graph a parametric set of equations is eliminate the parameter, turn it into a rectangular equation, and just graph that as usual, like if you had to do it by hand, and then go back and just figure out where it starts and where it ends, so you can figure out what direction it goes in. Would you have been able to graph this equation right there? By hand?
Well, maybe
Yeah, you
you can like,
Use the same method, yeah, it's just.
Yes, except that's right. It's just switched. You just have to switch your perspective like that. Yeah. And put it. Did you say put a title?
Put a title, this is top. Top goes here.
Okay.
Yeah, direction is relative.
All right. So let's say that we wanted to find the slope at a particular point. It's the same thing that slope always is. Slope is the change in y over change in x. Delta y or dy over dx. Okay, so whenever I take the dy dx of this, I'm taking the derivative of x with respect to x. That's just 1. Over here, though, whenever I take the derivative with respect to x, I'll have to implicitly differentiate. So I'll have a 2y dy dx minus 4 dy dx. Right? So factor out a dy dx, 2y minus 4, all that's equal to 1. So dy dx is? Now, I will say this right up front. This is not the preferred method, but we're trying to understand what's the derivative of a parametric set of equations is going to look like whenever we do it in terms of just the parameter. Okay, so it wants this at t equals 3, but I sort of have a problem here because there's no t in my derivative. So what do I do? Yes. So what was the y equation? T plus 1. So this is going to be a 4, right? 1 over, so dy dx such that t is equal to 3 is equal to, get rid of that, make this look prettier, 1 over 2 times 3 minus 4, 6 minus 4. Is that right? No, it wasn't 3, it was 4. Geez. 4. 1/4. So sometimes, though, they might ask you for the equation of the tangent line. We have the slope, then how would you find, let's say, the actual equation? What would you have to do at that point? So how do I find the point then? Yeah. The original set of parametric equations, correct. That's what we had to do in order to find the y coordinate of 4 over here in order to plug it into the derivative anyway. Yeah.
Question. Could you take the derivative of x with respect to y?
You could, but then that is, again, whenever you're changing your perspective, it's how does x change as y changes, which is not what slope is. Slope is always no, how y changes when x changes, right?
Take the inverse of it.
Okay, so there's all of that played out, and then here let's watch this animation for all of this. That's exactly what we just did, right? Okay, let's look at it parametrically though. Let's look at it with the parameters. So here, this function of x is a function of t. So let's take its derivative with respect to t. It would be, yeah, dx dt would be, yeah, 2t minus 2. All right, and then maybe you plug in, what was the point? It was 3. So if I plug in 3 in here, I would have 6 minus 2, I would have my 4. Okay, and then over here, let's do the same thing with the y. Its derivative with respect to t is just 1. Go ahead and stick a 3 in there. You still get a 1. Huh, look at those two numbers. What was our slope again at 3? It was 1/4. Is there anything we can do with these two numbers to get 1/4, I wonder? Yeah. So it is up top, it's the dy dt, and on the bottom it is dx dt.
Wait, question, why didn't you plug in t equals 3?
I did.
Yeah.
Oh, my bad.
Okay.
Oh, wait. Was t equals 3 the slope? Or was that the actual point value?
That's the t value. That's the parameter value.
Okay, why can't you just plug that into the original?
If you plug that into the original, you find the point. If you plug in, Joseph, if you plug it in here, you find the x coordinate and the y coordinate. Yeah, we're looking for the slope. So if you look at the formula right here, this dy dt over dx dt, you can almost think of it as the dt's cancel out and you have your dy dx that we're used to, right? So when I go back to whenever we did the slope this way, like this right here, that's not how you do it. That's extra because you would have had to eliminate the parameter, get a regular rectangular equation, and then take the derivative. That's too much work. Instead, we just do it like this, which is dy dt over dx dt. The second derivative, though, not so easy. All right, so derivative of parametric equations. So I'm going to show this to you. I think that I made this white so I can do this by hand so that you don't have to watch just an animation. So we're going to think of y as a function of x and then x as a function of t. So if I write that, y is a function of x. Write that as y is equal to f of x. But x itself. So as soon as let's finish the derivative part of this and then we'll pause and we'll eat, okay? We have a tower of pizza. Could we do the harmonic series with those pizza boxes?
Yes.
Like it was in that video?
Yeah. No, really.
They only gave us 14.
Yeah, the order said 14.
Oh, really?
Like I went in and asked. But
Man, I'm pretty sure it wasn't. Pretty sure it was 18. Okay, anyway.
yeah, we're going to start.
All right, so here we go. We're thinking of y as a function of x as usual, but x here is a function of t, so I'm going to replace that with what you see down here on the screen, this g of t. So if I were going to take the derivative of y here with respect to x, what would you have to use? You have to use the chain rule. So dy dx are is equal to, I would have yeah. So now let's put this back into like, help me out here. The other calculus guy. Leibniz notation. Yes, the Leibniz notation.
Newton.
Yeah, you want to do the Newton's notation? Okay.
Oh, yeah. I like that.
Okay. So this actually should have been dy dt. We're taking the derivative of y with respect to t. And This one here, this is the y's derivative with respect to the inside, which is the function of x. So we took it with respect to the g of t function, which was the function of x. Inside here is your dy marker work, dy dx. And then g of t, g prime of t is the derivative of x. We can see over here with respect to t. And now to solve for your dy dt, you have to divide your dx dt to the other side, and you'd have your dy dx is equal to on top dy dt over dx dt.
So what's that?
Yeah, based on the chain rule.
So this was like a way of proof, or we just proving something?
As in justifying that we're taking the slope or the derivative of y with respect to x for a parametric set of equations as the change in y with respect to time over the change in x with respect to time. Okay, when we are finished with lunch, we'll come back and we'll see how you're supposed to do the second derivative, because it's not obvious.
Why can't you do the second or like do the first?
Well, you can try, but you would fail.
Does it turn out to some weird things?
Yeah.
Turns into the wrong answer.